Welcome back. So we are going to follow this outline. The first thing we study is to review the statistical independence that we learned in chapter 2, and this is one of the assumptions for a binomial distribution. So we are going to utilize them. That's one of the key assumptions. Okay. Um, Remind yourself of statistical independence. If you forgot totally what statistical independence was, go back to the previous video, chapter 2 video, or like read through the slides in chapter 2. It is important, and it will be important in many videos in the future. So anyhow, so now suppose that A and B are independent binary random variables. They are independent, statistically independent. Then what is not correct? Choose one statement that is not correct. I use like conditional probability or intersection or union. So think about this. You should be able to answer this. If not, you have to review chapter 2, and the answer is D. Oops. The answer is D. So this was just to remind you of what we have learned. This is a special addition rule. This holds um, when A and B are mutually exclusive. But let's think about one. Probability of success in A is equals to the probability of success in A given that B is a success. So it means success in B does not affect the probability of A. So the outcome in B does not affect probability of A. So it's independence. And second, this is a special multiplication rule. The probability that A succeeds and B succeeds at the same time, A and B succeed at the same time, equals to multiplication of their respective probabilities. This is um, also this holds when A and B are statistically independent. And third is the same. The outcome of B, no matter what the outcome of B is, the probability of A success equals, does not change. And probability of A success does not change even if B fails. So all the other four imply that A and B are independent. They uh, do not interact. They do not interfere with each other. Anyhow, so it's an important concept, and we are going to use the second property of independent, statistically independent uh, random variables now. So when two random variables A and B are statistically independent, we had a special multiplication rule. A intersection B is multiplication of two probabilities. Now we may extend it to more than two events. When you have three, it it holds in the same way. Just you have more multiplications. It can be extended to many more, like does not matter. If you have 100 statistically independent random variables, you can have 100 product of 100 probabilities. So it's easy to understand. It's not that difficult to understand. Simple extension. We are going to use this property. This is the assumption. The assumption of the for the binomial distribution implies this kind of manipulation. We are going to do this. Okay, now we will start with an example with two reservations. So our goal is to understand 10 reservation case, but let's start from two reservations. Still, it's easy enough, but it's important to see the patterns, what changes when you increase the number of reservations. So now simply consider that there are two passengers who booked a flight, or A and B do not know each other, and the probability of cancellation is 10%. for A and for B, and cancellation is independent across reservations. So even if A cancels, it does not affect B. A and B do not know each other. Then what is the probability that A's reservation is canceled but B's reservation is not? A canceled but B not. What is that probability? It's simple. Do it. Stop. Pause the video, and I will turn to the next page at like 3, 2, 1. So, by the way, I will use this notation. Cancellation will be 1, denoted as 1, and non-cancellation will be denoted as 0. So 1 for cancellation, 0 for non-cancellation. It's typo. So B equals to 0 if B's reservation is not cancelled. Sorry for the typo. I will fix it. Then because we know the probability of cancellation, automatically implies probability of non-cancellation is 90%. It's cancellation 10%, non-cancellation 90%. So intuitive, straightforward. Then now, using the statistical independence assumption, we are looking for probability that A cancels. A equals to 1 means A cancels, but B does not cancel. And they happen at the same time, right? Two events at the same time. And this probability of intersection can be written as a multiplication. Probability that A cancels times probability that B does not cancel. So this probability is 0.1, this probability is 0.9. The answer is 0.09, which is 9%. So the answer is C. It's quite simple, right? It's pretty easy. Now I will tweak this. Almost the same question. Say, why is the number of cancellations of the 2 reservations? Still, we are considering only 2 reservations. So y is a binomial distribution, the number of cancellations. And all the parameters are the same. Probability of cancellation is 10%, and also independent across reservations. Then what is probability that y equals to 1? Which means probability that only 1 reservation is cancelled of 2. Try this. Think about this. It's a little bit more tricky. Still, you can do this. You have all the knowledge you need to answer this question. Try this more carefully, and I will show you the answer. 3, 2, 1. What you need to do here is you can make, like, it'll be the best way to understand this problem is to make a 2x2 table. So for A, there are 2 possible outcomes, 1 or 0. And for B, also there are 2 possible outcomes, 1 or 0. So if you combine them, there are 4 different possible outcomes. We have done this a lot of times in chapter 1, right? In chapter 1, we studied what's going on in this example, in this kind of example. Anyhow, so this outcome means A cancels and B cancels. Here A does not cancel, but B cancels. Here A cancels, but B does not, and A, B both do not cancel. So there are 4 possible outcomes, 2 by 2, and we are interested in these 2. Y equals to 1 means only one of them is cancelled, which means either A cancels or B cancels. So then, to calculate the event of probability of this event, you have to sum the probability of the outcomes in that event. So the probability y equals to 1 is this plus this, right? This probability plus this. And we already calculated this probability. It is 0.1 times 0.9. And using the same idea, you can calculate the probability of this event, right? A does not cancel, but B cancels. Also, A does not cancel, so 90%. B cancels, which is 10%. So 90% times 10. We get this. And in the end, you add two numbers which are the same. So zero point 0.1 times 0.9 is the same as 0.9 times 0.1. So we are going to write it as 2 times 0.1 times 0.9, right? So that is like doing the math. It's not that difficult to do the math. The answer is 18%. It is not that difficult. And one thing you have to understand here is that this answer to this question is 18%, but previous question was 9%. So the major difference is here in this question, in the former question, I specified who canceled and who not. So you know who canceled and who not, but in this question, in a binomial distribution, you don't know who is canceling. You just know the total number is 1. The cancellation is only 1. And then the probability is different from the former probability because you have to consider all the possible cases. Who is canceling, who is not, and it could be A or it could be B. Then you have to calculate the probability for each case, and in the end, you have to add all the possibilities. This is the tricky point, and this is the first thing you have to understand a binomial distribution. Okay, in the next video, I will start with 3 reservations. We are going to consider 3 reservations case. So see you in the next video.